I'll start this video with the hierarchy system of measurement. Okay, so in other words, there are different levels for geographic data sets. I mean, this hierarchy system is not exclusive to um, spatial data analysis, is not exclusive to geography, but since we're talking about statistics with the context of space, okay, so here, let's say, uh, I'll just use some examples from geography to address these different levels. So the lowest level is called nominal data. Exhaustive and mutually exclusive data are assigned to one and only one category, this type of data cannot be ranked or ordered. For example, soil types, presence or absence. Okay, a more specific example would be using different numbers for different ethnic groups in demographic geography. Okay, for example, we can assign value 1 to white, value 2 to black, value 3 to Asian, value 4 for Latino, right? So we have 4 values here, but these values cannot be ranked, right? It's meaningless to just rank different ethnic groups, right? If there is population data, of course you can rank them, but I mean, for these numbers only, they are only representing different ethnic groups. It's nonsense to just simply rank them, right? And of course, you cannot do any calculation with them. If 1 is for white, 3 is for Asian, what's the meaning to calculate the difference between 3 and 1? It's meaningless, right? Asian minus white, what does it mean? It's meaningless, okay? So this is nominal data. They are basically names, okay? White is not very convenient when you're dealing with data sets because it's a string, right? So we just assign a number to it. 1 represents white, right? So it's nominal. So second, level 2, let's just say level 2 is ordinal data. They can be strongly ordered. Data are placed in a particular position of a ranked sequence, which means that compared to nominal data, at least ordinal data can be ranked. For example, 1 for a high school diploma, 2 for bachelor degree, 3 for master degree, 4 for PhD degree. Of course, you can rank them by the level of education, right? So data can be compared, but the magnitude of difference cannot be determined. There could also be a weakly ordered ordinal data. Data are placed in categories which are rank ordered. Data within the same category cannot be differentiated. Okay, and the distance is meaningless. Okay, so if 1 is for high school diploma, 2 is for a bachelor degree, 3 is for a master degree, it's meaningless to calculate the difference between 3 and 1 or between 2 and 1, right? So you can order them, but you still cannot do other calculations such as calculating the sum of them, the difference of them, multiplication, or anything else. Okay. So next level is interval data. The magnitude of difference between different values can be determined. The origin or 0 is arbitrarily determined. Distance is meaningful, but product and ratio are not defined. For example, temperature in Celsius degree or in Fahrenheit degree, but not in Kelvin. Okay? Why? Temperature is tricky. Let's talk about temperature in Celsius degree or Fahrenheit. So let's just say for city 1, for a specific day, for city A, for a specific day, city A's temperature is 20 Celsius degree. City B's temperature is 10 Celsius degree. You can see that the difference of temperature between these two cities is 10 Celsius degree, which means difference or distance is meaningful between these two values, right? But Ratio is nonsense here. So city A is 20 Celsius degree, city B is 10 Celsius degree. Can you see that city A is twice as hot as city B? We don't say that. When we're talking about temperature, especially in Celsius degree and Fahrenheit, difference is meaningful. Multiplication and ratio is meaningless. We don't use these values that way. Okay, but Kelvin is different. Kelvin temperature has another name, kinetic thermal temperature. Kelvin temperature is an absolute temperature. Compared to Celsius temperature, or say Celsius degree or Fahrenheit degree, 0 is meaningful for Kelvin degree. You may ask, what do you mean by meaningful of, meaningful 0? 0 Celsius degree and 0 Fahrenheit degree, these two 0 values, okay, they are not absolute 0. For example, what's the definition of 0 Celsius degree? It's the temperature when water begins to freeze. Okay, it's arbitrarily determined. I'm not sure about Fahrenheit, but it's the same idea. So they are arbitrarily decided. You would ask, what if some 0 is absolutely determined? When a 0 is absolutely determined, 0 means none or nothing. Okay, that's the trick. So let's talk about Celsius degree. 0 Celsius degree doesn't mean there is no temperature. 0 Celsius degree is still a temperature, right? You would ask, when is 0 meaningful as temperature? 0 Kelvin degree is absolute 0 temperature. 0 K, 0 Kelvin degree is something ideal. It means that when the temperature is 0 Kelvin degree, there is no temperature. That 0 is an absolutely determined 0. It means that no molecule moves, which is not possible in real world. And we're trying to make absolute 0 degree in labs, but so far it's not possible because it's beyond the scope of physics we know right now. So temperature, when we're talking about temperature in Celsius degree and Fahrenheit degree, distance is meaningful. Our ratio is nonsense. Ratio doesn't make any sense. So this is interval data. But when we're talking about temperature in Kelvin degree, it's not interval data, it's ratio data, because the 0 in Kelvin degree is an absolute 0. When we say 0 K temperature, it means there is no temperature at all. Okay, next level, the highest level of data, ratio. The origin of 0 is naturally or non-arbitrarily determined. Distance is also meaningful, and product and ratio are defined. For example, let's talk about population. Say city A has 0 population, which is not possible. I know. Let's just assume that, right? There is a ghost city. There is no population there. This 0 is absolute, is non-arbitrary, because there is no people. There is nothing. And say, let's just assume that, okay, city A is not a ghost city anymore. It has a population of 10 million. It's a big city. But city B is even larger. City B has a population of 2 million. So the difference between this city in terms of population is 2 minus 1 equals 1 million people. So distance is meaningful, difference is meaningful, and ratio is meaningful. We can see here that city B has twice population as city city A, right? So 2 divided by 1. Population of city B divided by population of city A. Now here, ratio is meaningful. right? Population has been doubled when you move from city A to city B. Okay, and here example, like I mentioned before, temperature in Kelvin, okay, is racial data, is racial measurement. So here I organized this stair system, right? Hierarchy system, or say that. So the highest step is racial data, 0 is meaningful, or we say we have a meaningful absolute 0. For interval data, distance is meaningful, ratio is nonsense. Ordinal data, you can rank them, but you cannot do anything more than that. For nominal data, these data values, they are simply names. You cannot rank them, you cannot do any calculations with them. Okay, and for the bottom two levels, we call them categorical data, and for the higher two levels, we call them numeric data. Okay, and the lower the level, the less calculation you can do with the data. And here is another table telling you what you can do and you cannot do with nominal data, ordinal data, interval data, and ratio data. I'm not saying that you should memorize them, but in future, when you are facing different geographic data sets, when you're looking at a huge table with different entries and columns, the first thing you need to be sensitive about is the type of data. Say for column 1, it's for population, it's racial data. You can do anything with it. Column 2 is for ethnic groups. You have different values, but according to ancillary data, each value is associated with a specific ethnic group. Then you know, okay, this is only names. These values are names. Okay, it's meaningless to calculate anything with them or rank them. Okay, so this part is levels of measurement is something you should carry in your mind, carry with you when you are dealing with geographic data sets. Okay. So then I want to talk about different measurement concepts, especially the difference between precision and accuracy. Okay, so precision is the expression of the exactness associated with a measurement. Number of decimal places or significant digit in a measurement can be used to address precision. Okay, fake precision in calculation should be taken care of, or you should be careful with so-called fake precision in calculation. So here is a joke. Okay, it's a joke, but it's a joke about precision or fake precision. A tour guide at a museum says that a dinosaur skeleton is 100,000,005 years old. You see here, why 5 years old? Okay, here comes the punchline. Because an expert told him that it was 100 million years old when he started working here 5 years ago. So 100 million plus 5 is 100 million and 5. Here, this is a joke, but this 5 years is something we call fake precision, because compared to 100 million, this 5 years is just too tiny to talk about, to mention. Okay, so sometimes precision should be expressed at a specific level. For geological year, million years is meaningful. 100 million years is meaningful. The change of mountain, the change of the shape of the land, the shape of the ocean. When we're talking about geology, when we're talking about how old a dinosaur skeleton is, we are talking about time at million years level. 5 years is just not good enough. Okay, so in your research, be careful with that. Sometimes it's not just necessary to be too accurate. Okay, especially your data is very big. Is very big. Okay, so yeah, here is another example showing you precision. This is a ruler, and you can see that precision level for this ruler is from 0 to 1 centimeter. There are 10 measurements, right? So precision level is 1 millimeter, okay? And similarly for this specific segment with different precision levels, we can say it's 2 centimeters. Obviously, the precision is not high compared to the second one because for the second measurement, you used maybe a more advanced ruler, okay? You have ratings at millimeter level, so you can tell it's 2.2 centimeter, right? It's more precise than 2 centimeter. Or you have an even better ruler. You can just rate uh, the value at 1/10 millimeter. Then you can say, okay, more precisely, this segment is not 2.2. Instead of that, it's 2.23 centimeter. So what's the interesting part about this measurement is that the pursuit of precision is endless. I mean, if you continue to improve the precision of your instrument, it could be 2.231. It could be 2.2314. Is there an end? No, there is no end for this process. Okay, as the science develops, as you have more precise, better instrument, you can always make this precision higher and higher. Okay, so it's a simple segment, but the measurement of this segment is endless. Okay, okay. Accuracy. Accuracy is different from precision. So it is used to address the extent to which system-wide bias is present in the measurement process. Okay, closeness of results, computations or estimates to true values. So here, let me just give you a summary with accuracy and precision using these 4 targets. So the vertical is for precision. Okay, the higher the better precision you have. The horizontal axis is for accuracy. Okay, it moves from left to right. Okay, the further away from the origin of accuracy, the higher the accuracy. So if a shooter has very low precision and accuracy, the bottom left target is the result. So 1, 2, 3, 4, 5, 6, 7, 8, 8 shots. None of them is close to the center of the target, which means that the accuracy is pretty low. And all these shots, they are far away from each other, which means the precision of the shooter is bad. So it's bad, okay? So if the precision of the shooter is good, but the accuracy is not very high, this is the situation. All those shots, they're very far away from the target, from the center of the target. But at least they're together, they're very close to each other, which means there might be something wrong with the gun, the aiming system, right? So, but at least the precision is good. All these shots, they're close to each other. So on the other hand, if the precision is low but the accuracy is high, you can say that relatively these shots, they are not very close to the center of the target. But yeah, close enough compared to another shooter that has very low accuracy. These shots, they are closer. They're closer. At least they're closer to the center, but they are not clustered. Okay, they are. I mean, these 8 shots, they are away from each other. So if you have a very good sharpshooter, right, a sniper, very high precision, very high accuracy, then you can say 8 shots, they all hit the center of the target, which means the accuracy of them is pretty high. And all of them hit the center of the target, which means precision is very high. Okay, so next time when you are confused about the difference between precision and accuracy, try to memorize this very simple figure here. Okay, okay. Okay, now let's talk about some other basic aspects of geographic data sets. For example, planet distance. Usually, the distance we talk about in real life, and the most commonly used concept of distance in geographic data sets is Euclidean distance, right? Is the actual distance between two locations, right? For example, we have this Cartesian two-dimensional coordinate system with x and y. So since x and y are defined, each location can be addressed by a pair of coordinates x and y, right? So for example, we have two locations here. Location one, coordinates xi, yi, location 2, or location j, xj, yj. Okay, so how to calculate the distance between them, dij? We simply use very simple geometry. We can draw a triangle here and use the feature of triangle to calculate the Euclidean distance, the actual two-dimensional distance between them. Yeah, that's Euclidean distance. And in geography, we have other definitions of distance used for different purposes. Okay, I'm not going to go deep about purposes, but here I just want to mention a very simple, widely used non-Euclidean distance. It's called Manhattan or city block distance. Similarly, I mean, not similarly, exactly we have exactly the same locations, dot I, dot J, okay? The Manhattan distance is defined by this formula, Dij, okay? This time Dij is not Euclidean distance, is city block or Manhattan distance. Is the absolute value of the difference between xi and xj plus the absolute value of the difference between yi and yj. What does it mean? It means that there is only one path if you want to go from point I to point J. You have to move along X first, right? When your X value reaches the value at Xj, you have to go along exactly the direction of Y to get to location J. So how long did you travel? You calculate this part of the distance first, and then you calculate this part of the distance for for the second part, right? So which means that you travel to the right and you travel to the north, or you travel to the east and you travel to the north. So Manhattan distance, it is called city block distance. It's meaningful, right? For example, here we have a block. Let me draw this simple block here, right? We have a block here. And say you cannot penetrate this block. This block is occupied by a very huge building. You cannot just go through the building to travel from location I to location J. So how to travel? You go along one side of the block, then you go along another side of the block to get to location J. So how long did you travel? You use this formula to calculate, right? So city block distance. I would say this is just a simple example telling you that there is non-Euclidean distance, okay, for planar distance. In geography, in your research, in your work in future, try to be clear with that. When somebody is mentioning distance, usually it's Euclidean distance, but you may want to ask, what distance are you talking about? The real distance or other distances are defined arbitrarily. Okay. Okay. Next, let's talk about two views of geographic world. The first view is called entity view. We consider that there is this empty space, and anything else within this space, existing space, they are discrete objects. And there are well-defined boundaries to differentiate different or discrete objects. And the second view is called field view. We consider the space, we use another word. The space is occupied by continuous fields. A field can be a square, can be something with different shapes, but the space is continuous and it's not occupied by discrete objects. It's occupied by fields. Okay, these fields, they are adjacent to each other, so together they form the whole space. And we have different various variables, and there are infinite numbers of locations. Infinite numbers of locations is hard to implement with geographic data. We will say that, but we have proximities to simulate infinite numbers of locations. Okay, associated with entity view and the field view, we have vector model to address space, or we have raster model to address space. Vector model is associated with entity view, because when we're talking about vector data or vector model in geography, we have points, we have lines, we have polygons. Each point or each line or each polygon is a discrete object. For example, a tree as a point, a house as a point, independent from each other, discrete. Line, polygon, similarly. Okay. On the other hand, raster model or raster data is associated with field view. Okay. And usually when we're talking about raster data in geography, it's most likely remotely sensed data, or say an image. An image is actually a space occupied by fields, and each field is actually a pixel. These pixels, they are adjacent to each other to make sure there is no space unoccupied within an image, right? And you can consider each pixel as a discrete object, but when we're using remotely sensed data to address geographic problems, there is no so-called point or line or polygons within our image, because each pixel can be occupied by multiple things. Within each pixel, there could be a tree, a segment of road, and maybe there is also a small building. So you cannot differentiate different real-world discrete objects in raster model. And again, a polygon in a raster data model, for example, a huge building in a remote sensing image could occupy multiple pixels, and maybe one extra pixel, but part of that extra pixel. So there is no strict boundary defined in raster data. Of course, you can use ArcGIS to create an arbitrary boundary, but it's arbitrary. It's not well-defined boundary. What is a well-defined boundary? For example, you want to draw a specific area for forest in raster in a raster data set. You just use line segments to form a polygon and use that polygon to address the forest. That polygon has very clear, well-defined boundary. That is well-defined boundary. Okay, it's not happening in raster models. In raster model, we can address continuous variables such as elevation and temperature, or discrete variables. For example, the land cover of a pixel, or a land cover for a specific area, or soil type, right? These are discrete variables. Continuous variables such as elevation, temperature. So there is no right or wrong peak of models when you're dealing with geographic data sets. Maybe sometimes there are. For some problems, you need to use vector data to address. For some other problems, maybe you have to use raster model to address. But what I want to say here, is that there is no, how can I say? There is no absolute good or bad about vector model, between vector model and raster model. You always want to choose the more suitable one to serve your purpose. Okay, so when you are dealing with, say, urban planning, right? You want to know exact the spatial configuration of buildings within a specific city. Then vector data is better because there are well-defined, accurately defined boundaries. So it's very easy to differentiate, to recognize buildings, trees, house, roads, and rivers within the city, right? On the other hand, if you're working at a very high level data, for example, you want to address something at state or even national level, vector model could be very complex. And on the other hand, for example, you want to address something continuous in value, for example, elevation data. You can use raster data to do that. There is a specific type of raster data called digital elevation model data, DEM data. It can only be addressed, elevation can only be addressed. Let's just don't make it that absolute. Elevation is better addressed with DEM data, which is a type of raster data. So each pixel has a specific value, and that value is for the elevation of that part in the real world addressed by that pixel, of course. Okay, so two models for geographic data, they're associated with two views of geographic world. And example here, a real world right here is a river. Do not judge my drawing, okay? I tried. And here is a house, here is another house, several trees here. If you want to use a vector model to address them, so a line feature can be used to address the river. It's a linear feature, right? A point, another point, 2 points, they're good enough to address two houses, right? And two other polygons, they are used to address two woods or forests, right? And on the other hand, raster representation, right? The whole area, the same area is divided into small field, and each field can be considered as a quadrant or say a pixel if this is a remotely sensed image. So yeah, for all those pixels without anything inside, they're just empty, right? If this pixel is occupied by a house, give it a value, house. Usually we don't use that. We use a specific value, say 1 for house. That's nominal data we just mentioned, right? Another house and river, multiple pixels, they're actually trying to address this river, okay? And T for trace, okay? So you can say, depending on your purpose, you could use vector representation, you could use raster representation. So think about it next time when you're trying to describe geographic world with geographic data sets. Should I use vector model or should I use raster model to address the same area? It all depends on your purpose. And for the last slide of this for this lecture, I want to talk a little bit about the geographic data input, right? And it includes data collection, right? And the data conversion. So data collection means the collection of raw data, okay? Usually field observation and sampling, right? Human surveys and interviews. This is more like human geography, right? You design some questionnaires and you of course you have to design some specific sampling method, and you go to the streets and you ask people questions, right? Ground surveying, remote sensing, which means that sensors there in the sky not necessarily outside of the atmosphere of the Earth, because now we have drones, we have aircraft for remote sensing, right? But you should know, remote sensors, they're just like eyes hanging in the sky, looking at the surface of the Earth and trying to collect information, collect data. Global positioning systems, this systems, they are formed by different satellites flying outside of the Earth, right? And what they are trying to provide is not the category or the value or variables from the surface. They are trying to tell you positions, right? But yeah, maybe you can say coordinates, they are still values from the surface of the Earth. Yeah, right. Okay, you can say that. But yeah, GPS is also a data input, right? GPS systems, they are collecting data. Data conversion, digitizing. What is digitizing? So we see here, right? It's a house. Obviously, in GIS software, you cannot just draw a house to tell computer this is a house. It's not necessary. You just need to digitize this house. How to digitize? Use a point to represent it. Done. That's digitized. How about this river? Do you have to just draw two lines to address the width of the river at different segments? It's not necessary. You just need to draw a line feature to tell the computer the specific direction of the river. If you want to tell the computer the width of the river at different parts of the river, of course, you can create another column for that, right? This is digitizing. For example, this forest here, you use the polygon to digitize that. Similarly, for raster data, I mean, this whole space is divided into small pixels. That's actually digitizing, right? And then you assign different values to different land cover types. That's another level of digitizing. So digitizing means that you convert everything in the real world to something can be stored on your hard drive, right? So that's digitizing. Scanning, scanning, you can use an instrument to scan a map, right? When there is a hard copy map, when you scan it with a scanner that's scanning, it's actually another type of digitizing, right? When you're trying to use satellite sensors to observe the surface of the Earth, if you have ever enrolled a remote sensing entry level, entering level class, you should know that a lot of sensors, not a lot of sensors, all sensors, they are scanning the surface of the Earth using different methods. Okay, but since we're talking about data conversion here, scanning is actually a pretty good data conversion method to transfer hard copy data or analog data to digital data, right? The example I mentioned before, scanning a hard copy map, use a scanner, is an application of data conversion. Your hard copy map is analog data, or it's something cannot be recognized, cannot be addressed by your PCs. But if you use a scanner to scan it to create a PDF file or a picture file, then it can be stored in your PC. It's data conversion from analog data to, or say, hard copy data to digital data. Okay, that's all I want to talk about geographic data. And the next lecture, I'm going to introduce fundamental mathematical notations to prepare you for the rest of the semester. Okay, thank you.